matched filter. So this is a topic from your second module. Okay, we'll see the contents. So we'll start with the system model for a matched filter, then introduction, then we'll define the objectives, then noise analysis, how we are maximizing SNR and the result for the matched filter. So system model. So the basic problem with a digital communication system is to detect a pulse transmitted over a channel corrupted by the additive white Gaussian noise. So we have studied the pulse amplitude modulation system, PAM. So once we get the pulse signal, it needs to be transmitted. So it is usually transmitted through a channel, and the issue here is the channel will have noise. This noise is modeled as additive, noise is modeled as random, and it is AWGN, that is additive white and Gaussian. So we have already seen what all these terms means. So now here our concern is to design a filter that will optimally detect a pulse transmitted over the channel that is corrupted by AWGN. So it is called a matched filter because we will see why it is called as a matched filter, because its impulse response is matched to the pulse signal. So basically here what we do is we will model the receiver as a linear time invariant filter with, so an LTI filter will have an impulse response. So this receiver is modeled as an LTI filter with impulse response h of t, and our aim is to find h of t which will make this receiver an optimum one. Okay, the condition for optimality that we will see. So this is the system model. So this receiver, the input to the receiver is y of t, which is actually the sum of x of t and the noise n of t. So this noise small n of t is actually a sample function of the noise random process capital N of t. So details we have seen it already in the previous lectures, details of this noise. So the input to the filter y of t is consists of the pulse signal x of t, which is corrupted by AWGN noise n of t. Okay. Now consider that p of t is the pulse signal, and we are considering only a single pulse. So the amplitude of the pulse, or the amplitude of our original PAM signal is A0, that is the first symbol. Its amplitude is A0, so it is converted to a pulse signal p of t. So that is a transmitted signal x of t, and we have seen y of t is equal to the output of the channel, that is the input to the receiver is y of t equal to x of t plus n of t, where n of t is a noise. So this is equal to A0 into p of t plus n of t. Now the received signal r of t is, so we know it is actually our receiver is an LTA system. So the output of an LTA system will be the convolution of input and impulse response. So the received signal r of t is y of t convolution h of t. So it is y of t minus tau h of tau d tau integral. So for y of t we will substitute x of t plus n of t. So rearranging we will get the last equation. So it contains a signal component and a noise component. So signal component is A0 into integral p of t minus tau h of tau d tau, and noise component is A0 into integral n of t minus tau h of tau d tau. So now we will see what is an optimal receiver. So at the receiver, what are our objectives? So our objectives are, we should maximize signal power, and the noise power should be minimum. So these two are the objectives. So that means that the signal to noise ratio, that is SNR, you know SNR is a ratio of signal power to noise power. It should be maximum. So we have to maximize SNR. The objective of the optimal receiver should be to maximize the signal to noise ratio at the receiver. Now we will see each of the terms. Signal power. So we have seen already the signal component. So it is A0 integral P of t minus tau h of tau d tau. So signal power is actually expected value of signal component square of t. So you can write it like this. So this P of t, h of t, everything is deterministic. So there is no meaning in taking expectation. So it is E of A0 mod A0 square. We know that it is the power of the data symbol, and the second time is the time itself. There is, since it is deterministic, taking expectation is not required, or it. So we will get the signal power as PD into integral minus infinity to infinity P of t minus tau h of tau d tau the whole square, where PD is the power of the data symbol. Now considering n of t. So we know that this n of t is a sample function of the capital N of t, the Gaussian random process. It is additive and wide with 0 mean and variance n0 by 2. Now consider that the noise at the output of the filter is n cap of t. So it will be n of t convolution h of t, since the filter is LTI. So which is equal to integral minus infinity to infinity n of t minus tau h of tau d tau. Now the mean of E of n cap of t. So we have already done this in the previous lecture. So it is E of integral minus infinity to infinity n of t minus tau h of t d tau. So it is equal to integral minus infinity to infinity expected value of n of t minus tau h of t dot is 0, because expected value of n of t minus tau is 0. And now to find the noise power or variance, E of n square n cap of t square. So it is E of n of t into n, sorry, E of n cap of t into n cap of t. So you can write it as two separate integrals. Now you can rearrange it like this. Since h of tau and h of tau cap are deterministic, we can rearrange it like this. Now we know that this first term is actually the autocorrelation of the noise, or autocorrelation of AWGN. So we know that this autocorrelation is actually an impulse function, and since it is white, since noise is white and stationary, it depends only on the time difference. So it is n naught by 2 delta of tau minus tau cap into h of tau into h of tau cap d tau cap. So rearranging, it is equal to integral minus infinity to infinity h of tau integral minus infinity n0 by 2 delta of tau minus tau cap into h of tau cap d tau. So this using the properties of the shifted impulse, integral of a shifted impulse. So it is valid only when tau equal to tau cap. So you will get plus n naught by 2 into integral minus infinity to infinity h of tau into h of tau d tau. So which is equal to n naught by 2 into integral minus infinity to infinity mod h of tau the whole square d tau. That is, a noise power at the output is equal to n naught by 2 into energy of the filter. Okay, the energy of the filter is integral mod h of tau whole square. Now our objective is to find h of t that maximizes the SNR at the output. So we know that SNR is equal to signal power by noise power. So we will substitute both the terms for signal power and noise power, that is signal power is. So we have already found out both the terms, we are substituting it here. Now in order to solve this, we will use an identity called Cauchy-Schwarz inequality, which states that integral minus infinity to infinity u of t into v of t dt the whole square. it will be always less than or equal to integral minus infinity to infinity u square of t into integral b square of t dt. So we are separating the integral and taking the sum, so that will be always greater, and this is equal when u of t is equal to k into v of t, which is obvious. And also you should note that this u of t and v of t should be energy signals, or it should be finite signals, it should be finitely integrable. Okay, so this Cauchy-Schwarz inequality is valid only for that. Now consider the signal to noise ratio at the output of the sampler, that is t equal to capital T. Now this capital T is the pulse duration. So we have to sample at each pulse duration to get the message. That means നമ്മളൊരു PAM സിഗ്നലിന് പൾസായിട്ട് അയക്കുമ്പോൾ ഓരോ ഡേറ്റ പോയിൻറ്റും കറസ്പോണ്ടിങ് ആയിട്ട് ഓരോ പൾസാണ്. അപ്പോൾ പൾസിൻ്റെ ഡ്യൂറേഷൻ ക്യാപിറ്റൽ ടി ആണ്. അപ്പോൾ ആ ക്യാപിറ്റൽ ടിയിൽ വെച്ചിട്ട് നമ്മൾ സാമ്പിൾ ചെയ്തിട്ട് ഓരോ വാല്യൂ എടുക്കണം. ഓക്കെ, so that is what we are doing here. So then SNR is equal to PD into integral minus infinity to infinity. So we are sampling at t equal to capital T. So it is P of t minus tau h of tau d tau the whole square by the noise power. Now applying Cauchy-Schwarz inequality to this equation. So SNR is less than or equal to PD into we are separating that integral. Now we can see that this h of tau is deterministic. So this h square of tau, integral h square of tau, that gets cancelled out. So SNR is less than or equal to PD by n naught by 2 integral minus infinity to infinity p square of t minus tau d tau. And now using Cauchy-Schwarz inequality, the maximum or SNR is maximum, or this less than or equal to becomes equal when u of t is k into v of t. That is applying here for SNR is maximum for equality, that is when p of t minus tau is k into h of tau, take k equal to 1. So that means for matched filter h of tau is equal to p of t minus tau. So that gives a very important result. A filter that maximizes the output SNR is actually having an impulse response which is matched to the input pulse. So we know that input pulse is p of t. P of capital T minus tau is actually the shifted and rotated and shifted pulse, or we can say that this h of tau, that is the impulse response of the filter, should be matched to the input pulse. Okay, at that case we will get the maximum SNR. നമ്മുടെ ഒപ്റ്റിമം ഫിൽട്ടർ അല്ലെങ്കിൽ ഒപ്റ്റിമം റിസീവർ എന്ന് പറയുന്നത് നമ്മുടെ ഇൻപുട്ട് പൾസിന് എന്താണോ കൊടുക്കുന്നത് അതിന് മാച്ച്ഡ് ആയിട്ടുള്ള ഇമ്പൾസ് റെസ്പോൺസ് ആയിരിക്കണം അതിന് വേണ്ടത്. എന്ന് വെച്ചാൽ എച്ച് ഓഫ് ടി ഷുഡ് ബി പി ഓഫ് ടി മൈനസ് ടി, ഓർ എച്ച് ഓഫ് ടോ ഷുഡ് ബി പി ഓഫ് ക്യാപിറ്റൽ ടി മൈനസ് ടോ. ദാറ്റ് ഈസ് ദിസ് impulse response of the filter and the input pulse that we are used to represent our data symbols, that both should be mapped. Okay, so that is the result. So the maximum SNR is equal to PD by n naught by 2 into integral minus infinity to infinity p square of tau d tau, that is, or it is equal to PD by n naught by 2. With this p of tau and h of tau are matched, so you can write it like this: PD by n naught by 2 into integral minus infinity to infinity s square of tau d tau. So that is why this optimum filter is called as a matched filter. The impulse response is matched to the input pulse. So now we will have an assignment which is based on this lecture. So these two questions are actually very important. They are usually asked for university exam. State and prove the properties of matched filter. That is the first question. Then analytically prove the equivalence of correlation receiver and matched filter. So we have studied in the last lecture that this correlation receiver is optimum for passband data transmission. So there is an equivalence between this correlation receiver and matched filter. So you have to do the derivation, that is small derivation. For both these questions you can refer the Digital Communication by Simon Haykins, the textbook. So chapter 4 you will have this matched filter.